Hello there, calculus students. Welcome back to our class. I just had a near heart attack because my camera stopped working, but it seems to be working now. This camera's like, it's hard to explain because you can't see a picture of the camera, but it's like falling apart. There's pieces missing off the sides and so on. Anyway, we're going to be doing now optimization problems, which is all story problems. Make sure you get a copy of the optimization problems handout. Now here's the deal. This is actually one of the most important things that people do with calculus. On the other hand, it's just story problems, and it's not going to be terrible ones. On the other hand, I know that sometimes people freak out about story problems, and that's a very understandable response. Let's do 3 problems. Now, honestly, the description in this section of the book is great. We don't need to... I strongly recommend that you go through and read this. I think it's section 4.6. I'm not quite sure what we're on. Anyway, optimization problems, because the chapter's really good, all right? Rather than work my way through a bunch of examples that are in the book and that they do a really good job explaining, instead I'm going to do some problems that are even-numbered problems from the problem set at the back of the chapter. And when we say optimization problems, what we're really doing is talking about finding the absolute max and absolute min of a function over some interval to solve a story problem. This is actually a big deal in calculus, and actually you did a lot of this kind of stuff in algebra too, using different techniques. But now you have the much stronger ideas about calculus and so on. So let me do a couple of examples that are even-numbered problems from the back of the chapter, and we can go from there. Alright, so the first problem I want to do for you is problem 316. And what was happening in this problem is a classic problem of optimization, and that is we're making a box. We're starting with a piece of cardboard. Now, this is a huge piece of cardboard. According to the problem, it's 4 meters wide by 4 meters in this direction by 2 meters in this direction. That's a big old piece of cardboard. And we're making a box out of it by cutting off corners here like this, a distance x. We're going to have to figure out x. And then kind of folding this piece up and folding this piece up to make kind of a box or a basket or whatever, which is not exactly how boxes and baskets are made, but okay, I understand what they're trying to do here. And what they want to do in this problem here is they want to figure out how to make the box with the largest volume possible. So we're going to make some kind of function here, a function volume, and it's going to depend on x, the size of the little corner that we cut out here. I mean, we could make a little bitty corner cut out and make a big flat box that's not very deep, or we could have made x pretty big and have a taller, narrower box or whatever. And the volume of that box is going to be determined by x. Okay, let's see. It's going to be width times depth times height or whatever. Well, one way in which, as we fold this up, one of its dimensions will be x. This side here will no longer be 4 meters long. It'll be 4 meters minus x, or 4 minus 2x. And this direction of the box won't be 2 meters long. It'll be 2 meters minus x, or 2 minus 2x. The volume of the resulting box will be this function right here. Alright, the next thing we need to figure out for this function is what its domain is. What do we care about for this function as far as what are answers of x that we would find acceptable? Well, x can't be smaller than 0. That doesn't make any sense, right? We can't like cut off a negative amount of the box. And for that matter, if you think about this direction on the box, the cardboard's only 2 meters wide. We can't cut off a meter over here and then cut off a meter over here. There'd be nothing left of the box. I would say our domain that we're worried about is between 0 and 1 meters for x. That's how much of the box we can cut off. It doesn't mean there aren't mathematically solutions at other places along the way. Those are just the ranges that make any sense. The interval that makes any sense. Alright, so we're trying to figure out how to maximize this function right here. When we want to maximize this function, that means we need to find, well, it's an extreme value. And we had the extreme value theorem earlier in this chapter here. And it told us that the absolute maximum or absolute minimum of our function will be found at one of a couple of different places. It'll either be found at one of these endpoints, or it'll be found at some critical point that is between these two endpoints. Alright, so we only have so many places to look for what is going to be our maximum, our value of x that maximizes this function. Let's try the endpoints first. Let's try, what is the volume if the distance we cut off x is 0? Well, let's see, that would be 0 times 4 minus 0 times 2 minus 0 equals 0. I'd like to think that our maximum volume of the box won't be 0. So I'm guessing this guy's out. But we'll have to watch, obviously. We have to try the other endpoint. That was where x was equal to 1. All right, that would be 1 times 4 minus 2, which is 2. 2 minus 2 is 0. Oh, it's 0. Once again, if we cut off a whole meter off this side here, you can kind of see what would happen, right? Our box wouldn't have any sides anymore. And so, okay, this is also probably out. So it looks like what we're going to need to do is we're going to need to find a critical point of this function so that we can then check there and see if that's the maximum. All right, how do we find critical points again? Remember, critical points are those places where the derivative of our function is equal to 0 or undefined. All right. In this case here, if you actually do all this multiplication out here, by the way, it works out to 4x cubed minus 12x squared plus 8x, as you can see on your handout there. Well, okay, that is our function. We need its derivative if we're going to find the critical points. So let's find the derivative of this simple polynomial here. It's just 12x squared minus 24x plus 8. All right. We need to find the places where this is equal to 0. Well, you are armed like nothing for ways to find that. You know about things like the quadratic formula, completing the square, factoring. You could use whatever you want. I found the values, I'm sorry, I have a t here, but this is an x. I did it with the quadratic formula, and I found that x is equal to 1 plus or minus, we'll write it 1 over the square root of 3, just because people get a little bit freaked out otherwise. All right, there are two critical points here. Now, remember though, we're only interested in the ones that are in the interval from 0 to 1, and the positive solution is 1 plus something here. That one doesn't fit in our domain anyway. So the only value of x that we're interested in is 1 minus 1 over the square root of 3, which if you plug that into a calculator, you get like 0.42265. All right, so according to what we did here, there should be a critical point at this distance here. And in fact, if you plug volume of 0.42265 into your function, you get the maximum size of the box. The box size of the box would be 1.5 some odd square meters, which is definitely bigger than 0 when we had, x was equal to 0 and when x was equal to 1. In other words, this is the local maximum. Now, we can actually check this using a graph. If you actually graph this original function that we had for volume, you get the graph that's at the bottom of page 2 in your handout. And that graph looks something like this. We're at x equals 0, the volume, here let's label that, that's x-axis, that's that volume as a function of x. At this point here of our domain, the volume is 0. This is over here at 1 comma 0. When x was equal to 1 meter, the volume of our box was 0 meters cubed. But there was some place along the way which happened to be equal to 1 minus the square, like that. And the answer was something like 1.53 or something. It just keeps going after that. But that was the maximum. That is the biggest box, that is the most volume, the greatest volume of a box we can make. We have optimized the volume of the box that we can make by cutting off the corners this distance here, which works out to like 0.42265 or whatever meters. Makes the biggest box possible. All right. Gosh, there were problems almost exactly like that back in Algebra 2. That doesn't necessarily mean you remember it, and the techniques they were using were different at that time, but this is a more general way to do such a thing. Let's do another example from your book. You have a very similar problem to this on the homework set, but you're gonna do, I think it's 317 for you, but we're gonna do 318 right now. I'll even label that up here. This is on page 3 of your handout. And the problem is asking, find two positive integers such that their sum is 10, and then maximize and minimize the sum of their squares. All right, let's not worry about the part about integers just yet. Let's just worry about the fact that we're talking about two numbers here, x and y, that add up to 10. And what we're trying to do is we have some function of that. Well, let's not do the function just yet. Now, when I said you have two numbers x and y and they add up to 10, that's actually just kind of like saying like pick an x. I mean, because once you know the x, y is just 10 minus x. And we don't really need to worry about what the y is. Once we have the x, we kind of have the whole answer. And what the problem is saying is it wants us to find this x squared plus y squared. Well, we don't even have a y anymore. That's x squared plus 10 minus x, the quantity squared. We want to maximize and minimize this. We want to find what is the biggest value of that and what is the smallest value of that we can get. But before we can do that, we need to think about the domain that we care about. Now, the problem says that they have to be positive numbers. I think that means that the x is going to have to be greater than or equal to 0. But also, I mean, we want the y to be positive too. It said they're two positive numbers. So for y to be greater than 0, we mean 10 minus x is greater than 0, and that means x is less than or equal to 10. So in other words, we're really only interested in the closed interval 0 to 10 for x. Okay, so we don't really have that big of an interval that we're even caring about in this problem. All right. Once again, we're trying to maximize and minimize this, excuse me, I have the hiccups, this relationship right here. All right, the extreme value theorem tells us that the extreme values will be either at the endpoints or at some critical points between those endpoints. Let's do the endpoints first. If we call this thing f of x, let's just say right here. F of 0 will be x is equal to 0, so that'll be 0 squared plus 10 minus 0 squared. That'll be 100. I don't yet know if that's big or not. Let's try the other endpoint. F of 10 is equal to 10 squared plus 10 minus 10, the quantity squared, which is also 100. Again, I don't actually know is that a big number or a small number, but I now know at the endpoints of our interval what the values of f of x are. All right. Now we need to go look for those critical points that are between 0 and 10. That means we need to find the places that are where the derivative of the function is equal to 0. Okay, so here's our function. Its derivative then is, well, let's see here. I'm going to save myself some steps here. And with a little bit of organizing, you can see that the derivative is equal to this. Again, I did all the steps in the handout. I just don't want to do it all right at this exact moment. All right? And we're saying, when is that equal to 0? Well, it's just a little bit of algebra to see that that happens when x is equal to 5. Okay, that is a critical point. If that's a critical point, we better find out what the value of f is at that point. That would be 5 squared plus 10 minus 5, the quantity squared. That's 25 plus 25 equals 50. So we saw at the endpoints the value of our function was 100. At this critical point, the value of our function is 50. I'm starting to think that I know what this function looks like. I think at x equals 0, f is equal to 100. I think at x equals 10, f of x equals 100. And someplace in between, at 5, the f of x is equal to 50. So I think the function comes through here something like this. And in fact, if you, did I make that graph? Yeah, it's at the top of page 4. That's in fact exactly what it looks like. We can minimize, we have two numbers here, x equals 5, so therefore y is equal to 5. If our values are 5 and 5, we have minimized x squared plus y squared. And if x is equal to 0 and y is equal to 10, or for that matter, if x equals 10 and y is equal to 0, we get that x squared plus y squared equals 100. We have maximized the function. All right, now remember that back at the beginning of the problem it said these had to be positive integers. Fortunately, it worked out that our endpoints and our critical point were at integers, and let's just hope it keeps working out that way. If it didn't, let's say the minimum had been at 5.4 or something like that, then I would have tried the integer on either side of it. Like I would have plugged in f of 5 and plugged in f of 6 and just seen which one minimizes the function. Okay. Hopefully that won't actually happen though on any of our problems. All right, I want to do one more for you. That's good. That people who don't like story problems are going to not like at all. But it's a good problem. This is about getting to an island. Now, it's a little hard to set this problem up at the beginning, so let me work on this here. This is problem 326 in the book. Again, on your homework set, you have similar problems. The way the book is setting up number 326 here, they're just drawing a rectangle here, and they're saying that there's some island over here. And the island is 1 mile, and here's the beach, okay, on this side. And you are right here, 4 miles from the closest point to the island. You understand what I'm saying here? Where like you could walk 4 miles this way and then row a boat 1 mile out to the island. All right, so there's sort of this rectangle here. Okay, we could walk along the beach and then row a boat out to the island. Okay, but that's not what we're going to do. We're going to exercise. We're going to run, and we can run at 6 miles per hour. And at some point, we're going to swim, and we can swim at 3 miles per hour. And what the problem is asking is, how are you going to get to the island the fastest? Okay? I mean, you could run 4 miles and then swim 1 mile. You could say, I'm not going to run at all and just swim directly from where you are to the island. But it should probably seem intuitive that it's going to make sense to like run part of the way and then swim to kind of cut the corner. You can run faster than you can swim, but you don't need to swim so far. There must be some distance along here that it makes sense to like cut this corner off. Okay? So what we are trying to do is we're trying to minimize the amount of time it takes to get to the island through some combination of running and swimming. All right, when I thought about this problem, I thought, let's call this little distance here x. The distance that you're like skipping by not running. The corner that you're cutting off. In other words, you're skipping x here and you are running this part, which is 4 minus x. The reason why I liked that is then that makes this side kind of simple. By Pythagorean theorem, that's just 1 plus x squared on that side. You're going to swim the square root of 1 plus x squared, and you're going to run 4 minus x. Could you have set the problem up other ways where like maybe you were making x this distance you swim? Yeah, absolutely. There's certainly ways you could have done it other than this. But that's the way I set this problem up. All right. So let's see. I'm going to run 4 minus x miles. And I run at 6 miles per hour. I don't know if you think through, this is going to be a dirt equation problem. Remember, distance equals rate times time. I want to know the time. So it's going to be distance divided by the rate equals time. All right, that's going to be a dirt equation type problem. All right, so the time I'm going to spend running is the distance I'm running. Well, that's 4 minus x over the speed that I'm running, which is 6. And I don't know, I'll just simplify this a little bit right here. In the same way, I can see how far I'm going to swim. And so the time I'm going to spend swimming is going to be the distance that I swim divided by the speed at which I swim. And the whole amount of time that I spend getting to the island, which will depend on x, because it depends on how much of the corner we cut here, is going to be the time I spend running plus the time I spend swimming. That's pretty cool. All right. What is the interval here? What values of x are going to make any sense? Does it make any sense to cut less than 0 off? Like to actually run past over here and then swim? No, of course not. Does it make any sense for x to be bigger than 4? Like we actually run this way first and then swim? No. Clearly the interval we care about is 0 to 4. We could cut none of the corner off at 0, run all the way to here, and then swim 1 mile. We could cut 4 off and just swim right from where we are, just walk right in the water and start swimming. Those are two possibilities. And the extreme value theorem tells us that the extrema, the absolute max and minimum of this function, will be either at one of these endpoints or at some critical point between the two endpoints. All right, well, I will, let's see here. On the back page is where we finally get to it, I think. Nope, wait, where was it? All right, at the bulleted list on page 5. That's where it is. Let's go ahead and try these endpoints here. How long does it take if the corner you cut is 0? You just went right here and you're right here. You plug in the values here and you will get, this is 2/3, and this will work out to 1/3, and it ends up being 1. It takes 1 hour to run the 4 miles and swim 1 mile. Let's try the other endpoint. T equals 4. I'm sorry, T at, if cutting corner was 4 miles. In other words, you just stopped right here and just swam straight for the island. And that works out to square root of 17 over 3, which is bigger than 1. That's clearly not minimizing our distance. Our time, rather. So far, the best thing looks like just not cut anything at all. Run all the way to this corner and then swim the rest of the way, but we still haven't checked critical points between 0 and 4. All right, so if we're going to do that, we got to find some critical points. Remember, critical points are the places where the derivative is 0 or undefined. Okay, let's find our derivative. Let's see here. 1/3, 1/2. It's a chain rule problem. Did I do that wrong? I might have a mistake on the handout. Hold on. Let me look at this here for a second here. If so, I'll fix the handout before I give it to you guys. Let's see here. So the derivative here is 1/6 plus 1/3 times the derivative of the numerator here. Okay, the derivative of that numerator is 1/2 times this to the negative 1/2 power times the inside's derivative. There we go. Okay. I just had a mistake in the way it was written. I'll fix that. Okay. So, this is 1/6 times like this. All right. Excellent. Yeah, I'll fix that handout before. There's just one typo in the version I have right now. All right. We are looking for places where this derivative is equal to 0. All right. Now, if you look on page 6 of the handout, you can see it took me 1, 2, 3, 4, 5, 6, 7, 8 steps before I was able to get this here, where I found that x is equal to 1 over the square root of 3, which is the same thing as square root of 3 over 3. All right. Which is, by the way, the same thing as about 0.577. Then, when I plugged that into my time function here, we end up getting 0.95 hours. In other words, if I cut off a distance of about 0.577 miles here, a little over half a mile, I run most of the 4 miles, but not quite, and then swim toward the island, I minimized my time it took to get to the island. Ooh, these problems are fun. I anticipate that there will be a lot of questions about these problems. There always are when we do story problems, and when I looked at my notes from previous semesters, I know that this is something that students both appreciated because they like applications of things, but also got a little stressed out because they weren't sure what equations they were working with and so on. And that is perfectly normal and acceptable in how we do things around here. All right. I think we have it under control, though. So we're going to go ahead and put this up on Google Classroom. You've got an exit ticket about this. You've got a homework set about this. You have over a week to do this assignment. And please let me know if you have any questions.